Okay. So we have, so I guess we should get started. I need to share my screen, so let me get on that. This one. Yeah, okay, there we go. Okay, so we need to finish up with section, I forget which section this is, I think it's 2.3. So we talked about the invertible matrix theorem last time. I think I'll type up a handout that sort of lists those things. And then we'll, like I mentioned before, we'll be adding to it as well. So that is an ongoing theorem. But let's see. So this was on the invertible matrix theorem. I don't think that's what the name of this section was, but essentially this is what it was about. And oops, I didn't put the section number. I wanted to do a couple of examples using it. So just quickly. Is there a quiz today? There is not a quiz today. And so in the future, we're going to be having quizzes on Thursdays instead of Tuesdays. This is not Tuesday, instead of Mondays. And so just so you know that, we will have a quiz on, what's that going to be? This Thursday, yeah. Right. Okay. Examples. Right. Okay, so first example, we could ask like whether or not a given matrix is invertible. So say we have this guy. Right? Okay. And basically when we're using the invertible matrix theorem, we want to find the easiest way to answer this question. And there's all of these equivalent ways of looking at this question through the invertible matrix theorem. But the easiest way to deal with this particular problem is, if you notice, column 2, the second column, is a multiple of column 1.
Wait.
Oh, oops, there should be a negative there. Now it's a multiple of column 1, right?
Okay, now it is.
Now it is, yeah. So we just take column 2 and we multiply it by 2. Or sorry, well, I guess we take column 2 and multiply it by 1/2, and that's equal to the first column. So that means that the columns of A are not linearly independent, right? Because we can write one as a multiple of the other. So columns of A are not linearly independent, which means that A is or is not invertible.
It's not.
It is not invertible. Yes, exactly. This means that A is not invertible. Right? Okay. So this was by, let's just say, by the invertible matrix theorem. Okay, and then let's look at another example. So consider an upper triangular matrix. I believe we defined this, but let's go ahead and well, maybe.
Pardon me.
So I'll go ahead and define it. So an upper triangular matrix is one where you have all entries below the diagonal are 0. Right? So it would look something, if you want to see an example, it would look something like this. Let's say we have something, I'm just filling in some numbers, but we have zeros below the main diagonal. So remember, this is the diagonal, and the reason we call it an upper triangular matrix is because we get this kind of triangle on the upper part of the matrix. And we could similarly define a lower triangular matrix, which would have zeros above the main diagonal, right? Okay. So this is an upper triangular matrix, and we could ask just a very general question. So when is a square upper triangular matrix invertible? Question mark. Okay, so hopefully you can look back at your notes for the invertible matrix theorem, right? And what do you think we should use to deal with this particular situation? We don't have that much information about the matrix, just that it's upper triangular, right? So which of the different conditions should we use?
Could you use the fact that it has n pivot positions?
Yeah, so that would be one way of looking at it. So another way of phrasing this question, so we can rephrase it as when does an upper triangular matrix have n pivot positions? And the answer to that is when there's no zeros on the diagonal, right? If there was a 0 on the diagonal, then that would correspond to a column where we don't have a pivot position, right? So this means that the answer is when there are no zeros on the main diagonal. So this is our answer. Right? Okay, so depending on the situation, you may want to use a different condition depending on what kind of information you have. It's really just a way of taking a question that's very important, right? Whether or not this is invertible, this matrix is invertible, and thinking about it in all these different ways. And we're sort of putting all of that information into one theorem. This is the big theorem of linear algebra, and it's sort of like the power behind these tools, because we have all of these equivalent ways of looking at the same problem, right? And some of them are easier to deal with than others. Okay. So we had a couple of examples, and you'll have more practice using this theorem. We do need to cover one more thing from this section, which was invertible linear transformations. Okay, come on. Let's see. Is it still upper triangular? Yeah, it is, in fact. So there's no condition on the numbers that lie above or on the diagonal. So you could have a whole bunch of zeros. It would still be an upper triangular matrix, right? So it's just saying that you have zeros below the main diagonal. Okay, cool. Oh. Yeah, technically yes, but it's a bit strange to say that the zero matrix is upper triangular. Yeah, but yeah, it does satisfy the definition, so it's fine. Right. Okay, so we're going to talk about invertible linear transformations. So this is invertible in the regular sense of like functions, right? Meaning that it has an inverse. And just remember that there's this correspondence between linear transformations and matrices, right? So we know that every linear transformation, so this is what, oh, oops. So recall, we talked about this before, every linear transformation has a corresponding matrix. A, so we can express our linear transformation as just multiplication by that matrix, right? So there's this nice correspondence. And also matrix multiplication corresponds to the composition of those linear transformations. So to make this more precise, if we have a linear transformation T, which is given by the matrix A times X, and we have a linear transformation S, which is given by the matrix B times X, and supposing that the dimensions are all fine, and we can do the composition of S composed with T, then that would be given by multiplication by B. Well, really, because we go outwards, it'd be multiplication by A and then B, but in this order, right? So we just multiply the matrices to find the composition, right? Okay. Now, a linear transformation is invertible. So invertible, right? If it has an inverse, so if, actually let's make it clear. So we'll say T maps Rn to Rn. It's actually necessary for it to be from Rn to Rn. Yes, as that is what that means, yes. Okay. Invertible. Okay. A linear transformation is invertible if there exists another linear transformation, we'll call it S for now, such that when we compose them, we get the identity. So this is really similar to our definition for matrices, right? So S composed with T of X just gives us back x. That's what the identity transformation would do. It doesn't change anything about that vector. It just gives it back to you. And also t composed with s is x, right? So you have to check both ways. So similar to, again, matrices, right? And if this is the case, so if this holds, then we say that S is the inverse of t, which would be denoted t to the -1, right? That's how we denote inverses of functions. It's also how we denote inverses of matrices. So same notation there. Maybe that should be in there, right? So denoted t to the -1. Okay, and then given that we have this info that we talked about right here, that a linear transformation corresponds to a matrix and multiplication corresponds to compositions of linear transformations, it shouldn't be too surprising. We could check, but I'm going to skip over that part. But at least it should make sense that if t is invertible and it has the matrix representation A, then
Then A is invertible.
what's that?
Then A itself is invertible.
Right, and that T inverse of X is equal to A inverse. Right, so this is, maybe I should include that as well. Then A is invertible and T inverse is equal to A inverse times X. So finding the inverse of a linear transformation just boils down to finding the inverse of the matrix that describes it, right? Which we learned how to do. Right? Okay. And this also goes the other way, that if A is an invertible matrix, then the linear transformation.
Can you go up a little bit quick?
Oh yeah, sorry. So I'll also say and vice versa. So if A is
Thank you.
invertible and T is given by A times X, then the transformation is invertible. Does S go from Rn? Oh yeah. Yeah, oops. Skip that. There we go. Also from Rn to Rn, yes. Okay, so let's do an example. Right. So consider a transformation T from R3 to R3 given by T equals A times X, where our matrix A will be the following. So 1, 0, 0, 0, 1, 1, 1, 0, 1, like so. And the question is T invertible? And if so, find T inverse. Okay, so equivalently, we want to know whether A is invertible, right? So we just take the method that we have for finding the inverse is to take our matrix and augment it with the identity matrix, right? We create something like this. So 0, 1, 1, 1, 0, 1. And then on the other side, we have 1, 0, 0, 0, 1, 0, 0, 0, 1. Right. And then we will row reduce this guy, and we'll end up with A inverse if it exists on the other side. If not, then we won't end up with, so we're going for the identity here. If we don't end up with the identity, then we know that there is no inverse, okay? So either way, this is the method that we should be using, okay? Right, so let's row reduce. So the first thing I want to do, I guess we'll take row 3 to, we'll replace that with row 3 minus row 2. And we'll get a 0 here, still have a 1 there, and we'll get -1. Nope, not there, sorry. We'll get 0, -1, 1. Okay. And so let's just fill in the rest of these and keep going with our, what's this called again? Our row reduction, right? So we just need to clear this 1 here, and then we should have the identity matrix on the left-hand side. So we just want to take row 1, replace it with row 1 minus row 3, and that will give us, like I said, we will have the identity matrix on this side. Now let's figure out what happened on the other side. Row 1 minus row 3 would be 1, 1, minus 1. Oh, 1. There we go. So that would be our inverse. That means that A is invertible with A inverse equal to this right matrix. So this guy, and so T is invertible as well. And T inverse is equal to this A inverse times X. So without writing it out again, I'll just put it that way. Okay, so this is going to be the same process as what we've been using to find the inverse of a matrix. And in fact, if we wanted to write out, okay, I'll actually just leave it there. Okay. So that finishes up this section, section 2.3. And we can move on. So we're skipping a couple of sections now and moving on to 2.8. So 2.8 covers subspaces. Okay. Let's go ahead and define what a subspace is. So it has to be a subset, meaning it's some smaller collection inside of your space. So it's a subset of Rn, right? We say that this is a subspace if we have a few things. So first of all, 0 is in H. So our subspace has to always contain the 0 vector. For any 2 vectors, U and V in H, we have that their sum, U plus V, is in H. So I'm using this notation. I don't know if I've mentioned this before, but this, just read, is in, or is an element of, but in is fine. Okay, so if we take any two vectors in the set H, their sum should be in H as well. And also if we take any vector, say U in H and any constant in R, then the scaled vector C times U should still be in H. Okay. So there are these three conditions. Essentially, it says that a subspace has to contain 0. So that's the first thing. And it also has to be closed under linear combinations. So anytime you take a linear combination of vectors in your space, it should stay inside of that space. Okay. So if you want to think about this, so this says that a subspace contains the 0 vector and is closed under linear combinations. So this way of saying this is just a convenient way of saying that the linear combinations do not like reach the outside of the subspace, right? Okay. So let's do some examples. So
Wait, so you can combine the last two statements to say like any linear combination of U and V are also inside H.
yeah, you could combine the last two. And maybe that's a little bit easier to remember. So whichever way is easiest to remember, just put it in those terms. Right. Okay, so let's look at some examples, right? So first of all, if we have a vector, say U, I won't give it an actual, I won't give it coordinates or anything, but okay, say we have a vector U in R2 and H is equal to the span of U. So remember that's going to be just all scalar multiples of that vector U. So it's going to be the line going through it, right? That would be the span. So H would be represented by this line here, right? We can check that it satisfies each of these three conditions, right? So 0 is in H because we just take U and multiply it by 0, the constant 0, and that is equal to the 0 vector, right? So that guy, that 0 vector is in the space. Also, if we take any two vectors, I'm going to use a different letter than U. So let's say we have, V and W in H. Well, if V and W are in H, then they are scalar multiples of U because that's the definition of this space. So C times, so I'm saying that we can write V as C times U for some C, some constant, and W, we can write it as D times U for some other constant. Well, they could be the same, but in any case, if we take the sum of these guys, that's equal to C times U plus D times U, and then this is just one of our properties of vector addition. We get, this is equal to C plus D, those two constants, times U, right? Which is definitely in the space H. Okay. And then you can similarly check that so for the third condition, that for any V in H and constant in R, that this would be in H. So check. Okay, so that means that this H, as we've described it, is a subspace. And in general, any span, so any subset that we can write as the span of a collection of vectors is a subspace. So we just get that from the definition of the span, right? It's just the collection of all linear combinations of those vectors. So if we took any linear combination of vectors, it would be inside the span, therefore inside the subspace. And then we always get that the 0 vector is in the span because of basically this argument that we gave right here, that we can multiply by 0, the constant 0, and get the 0 vector. Right? So this is somewhat important. Any span is a subspace. Furthermore, if we have H written as the span of some collection of vectors like this, then we say that H is the subspace generated by those vectors. Okay. So that was our first example, but we sort of expanded it to include a bunch of other examples because anything that we could write down as a span will be a subspace, right? Let's do another, let's say, more concrete example. Here, we're still in R2, but we're going to take H to be the set of vectors x, y, such that x times y is greater than or equal to 0. Okay, so what does this include? If we want to graph it out on our space over here, if x times y is greater than or equal to 0, that means either x and y are both positive or they're both negative, right? So if this, excuse me, if this is my x-axis and this is my y-axis, that means that you're either in the first quadrant where both x and y are positive, or you're in this third quadrant where they're both negative, right? So that's the space that is described by this.
Does it also include 0 because it's greater than or equal to?
Yeah, it does include 0. Yeah.
Okay.
So, yeah, so that's true. So the 0 vector is in H. So that's one condition. But just looking at this like graphically without actually doing any computations, we could see that if we were to take a vector, let me just redraw this so I can have a clean slate. So we know what our subspace is going to be. So if I were to take, say, this vector right here and this vector along here, both of those lie in H, right? So as I've drawn them, and we know using the parallelogram rule for vector addition that if we just put this one, that same vector right here, we get a little parallelogram, and the result will be u plus v. I guess I'll label these. So this one is u and this one is v. See that u plus v does lie outside of H, right? So that means that H is not closed under addition. And I guess in particular vector addition. So H is not a subspace. So maybe to make this more precise, so U and V are both in H, but U plus V is not in H. I'll leave that there. Okay. Okay. Another example. So this one's pretty basic, or simple, I guess. If we take H to just be the zero vector, only include the zero vector, well, clearly it does contain the zero vector, so that first condition is satisfied. Also, if you take any linear combination, basically you can only take multiples of 0, right? And that will always be 0 for any constant. So that means that, and if you want to write out the addition 0 plus 0, that's the only vector in this space. So this is the only addition you could possibly have, and that's equal to 0. So you stay inside the space. So this is called the 0 subspace. Right. Okay. So let's do, I think, one more example. Right. And this is just for visualization. So we already said that any span can be, or any span is a subspace. So we don't need to verify that this is a subspace, right? But if we think about what this is, like if we want to visualize it, this is going to be in R3. So our space looks like this. And it is just the first two coordinates are non-zero, right? And so it's any linear combination of those. So it's going to be the xy, if we use coordinates x, y, z, like this, it'll be the xy plane inside of R3, right? That's what this span describes. So it would, continue over here, but the way I've drawn it, it's like just this first quadrant-ish area. So what I wanted to say by including this example is just, you can think of this, your subspace, as a copy of R2 inside of R3. So that's the idea of a subspace, right? It's like a linear space, it's one of our Rn's, sitting inside of a larger space, right? Right, so the definition or the way that we've labeled this concept kind of makes sense, right? Yeah, so as we said, any span is going to be a subspace, and it actually turns out that any spanning set or any subspace has a spanning set. So any subspace can be written as the span of vectors, right? So they're sort of one and the same. And so we will, I guess, talk about that in a second. Do I want to do that first? Actually, yeah, I'm going to do this first. Okay, so this idea of a spanning set this is what we'll refer to as a basis. So a basis, just to write out in words and then we'll have a formal definition. A basis for a subspace is going to be a minimal, linearly independent spanning set. So by spanning set, I mean a set that spans the space, right? So more formally, we say that a collection of vectors v1 up to vk is a spanning, right, by minimal, I'm going to make that more concrete now. So v1 up to vk is a basis for a subspace if we have that, first of all, it actually is spanned by that set. So H is equal to the span of V1 up to VK. And furthermore, the V1 up to VK are linearly independent. Okay. So the reason why this creates what is called or what I referred to as a minimal spanning set is because this linear independence, this requirement that we have linear independence means we won't have, for instance, multiples of the same vector, right? And we also won't have vectors in there that can be written as linear combinations of some of the others. So there's sort of like a sense in which this is the smallest possible set that we can write because we're requiring that they be linearly independent. So we don't have any redundancy in our list of vectors, basically.
Oh, so like if they were like linearly dependent, then that means one of them could be written as
One of them would be unnecessary, right? At least one of them would be unnecessary. So yeah, this requirement that we have linear independence just sort of like will flush out some of the unnecessary parts. Right? Okay. So I just wanted to point out a basis for a subspace is definitely not unique. Right? There are many different bases that we might have for a particular space. So for example, we know that if we take in R2, just the two coordinate vectors, so 1, 0, and 0, 1, this spans all of R2, right? So we could see that we could just take any linear combination, get any vector in R2. But it's also the case that the span of 1, 0, and 1, 1 is all of R2. We could still get every vector written as a linear combination of these two vectors. So these are both bases for R2, but definitely not the same, right? Okay. Right, so we are going to go ahead and talk about the column and null space of a matrix. So these are special subspaces that are going to be pretty important, right? So these are the column and null space. Did I do column spacing, yeah, column and null space of a matrix. So these are subspaces that are related to a matrix, right? Okay, so say A is an M by N matrix. Then we're going to define two things. So the column space of a matrix is just the span of its columns. So it's kind of what it sounds like, right? Column space of A is going to be the span of the columns of A. And the notation that we use, so this is denoted col, C-O-L of A, like that. Okay. And we already know that if we can write something down as the span of vectors, that it will form a subspace. So we don't need to check that this actually gives us a subspace, right? We already know that by the way it's defined, it will definitely be a subspace. So let's just make a note. This is a subspace because it's a span.
Oh, this is how you formulate, write like the span of the columns of a matrix. The column.
Yeah. So now we have like a nice way of talking about it. We just call it the column space, right? Yeah. Okay. So the other space related to a matrix is called the null space. And this is the null space of a matrix is going to be the set of all solutions of the homogeneous equation. So this AX equals 0, this homogeneous equation that we've been talking about. And this space is denoted null, so NUL of A, like that. Okay, so it's a set of all solutions. It's not immediately obvious that this is a subspace, right? It's not definitely equal to the span of vectors. So let's just double check that this is a subspace. So a subspace, and so we can just check the conditions. So first of all, is the 0 vector in the null space of A? Well, we know that it is because the 0 vector is always a solution of this homogeneous equation, right? This always has 0 as a solution. Okay. And if we take two vectors u and v in the null space, that means, so maybe move this down a little bit. So if u and v are in here, what that means is that a times u equals 0 and a times v equals 0. So we can just look at a times u plus v. We want to know that this is equal to 0. That would mean that u plus v is in the null space. And we know that this is equal to, we can just distribute. So a times u plus a times v, each of these is equal to the 0 vector. So we do get the 0 vector out of this. So this means u plus v is in the null space if U and V are. And then lastly, we want to check that if we multiply by a scalar, that we get something in the null space. So if U is in the null space and C is a constant, then, well, since U is in the null space, A times U is equal to 0. Well, okay, we know that, so I'm not going to write it down. We're looking at A times C of U. Let's see. A U plus A V. So we know that individually, A times U, this piece right here is equal to 0. So we're just using this information right here, right? And then separately, we know that A times V is equal to 0 because V is in the null space, and then we just add those two things together and we still get the 0 vector, right? Okay, yeah, that happens. Okay, so let me get rid of these guys. So we're looking at A times C times U, and just by properties of matrix multiplication, we can pull that constant out to the front, and it's equal to C times A times U. And we know that A times U is just 0, so you get C times the 0 vector, which is still just the 0 vector. Right? Which means that C times U is in the null space of A. Okay, so we verified all three conditions. That means that this is a subspace. So the null space of A is a subspace. Done. Okay. One thing I do want to note. So just picturing our M by N matrix A, right? So we have M rows and N columns, right? Just, oh yeah, just write it like this. Okay, so knowing that the column space is so it's the span of the columns, right? And we notice that each of the columns of A is a vector in Rm, right? So just picturing a column right here, it will have M entries because there are M rows, right? So that means that the column space of A is a subset. So this is how I write subset of Rm. This means subset. So it's just contained inside of Rm, right? And the null space is the collection of solutions to the homogeneous equation, and any solution is going to be a vector in Rn, right? Because when we write down Ax equals 0, the size of X has to match, or the number of entries in X has to match the number of columns of A in order for that matrix multiplication to be defined. So our null space is a subset of Rn, right? So they're actually living in two separate spaces, right? So that's something to notice. Okay, so let's do an example, right? Yeah, of finding the column space and null space. So if you're just given a vector, sorry, if you're just given a matrix, you would want to row reduce it before you try to figure out what the null space and column space are. But just to avoid doing all that tedious work, just to do an example, I'm going to give a matrix that is already row reduced, right? So here we have 0, 0, 0, 1, 0, 0, and minus 3, 2, 0, 0, 5, minus 1, and 0, 0, 1, 0. Okay, so suppose we have a matrix and it row reduces to this form, right? Then we want to determine the null space and column space of A. Okay, so let's start with the null space. So we want to find all solutions of the homogeneous equation, right? And this is already row reduced. So we have some practice doing this. We want solutions of, so we're working on null space of A right now. We want solutions of AX equals 0, right? And so we can just use the fact that this is already row reduced. And if we set this A times X equal to 0, what we would get out of this system right here is X1 minus 3X3 plus 5X4 equals 0, right? That's from the first row. The second row tells us that X2 is 2X3 minus X4 equals 0. The third row tells us that X5 is just 0. And then we have two free variables, right? We have X3 and X4 are free. And so what we usually do to write down this solution in parametric form is we rewrite X1 and X2 in terms of those free variables, right? So X1 becomes 3 times X3 plus, or sorry, minus 5 times X4, and X2 is negative 2X3 plus X4, like that. And so to write down our general solution, X, just writing out each of the entries and replacing it, we get 3X3 minus 5X4. For X2, we get negative 2X3 plus X4. And then we have X3 and X4 are free variables, and X5 is always 0. So we just replace that with 0. And then we split these into two vectors, right? One corresponding to X3 and one corresponding to X4. So the first vector will be X3 times 3 minus 2, 1, 0, 0. And X4 will be minus 5, 1, 0, 1, 0. Okay, so this is our solution, and these vectors will span the null space, right? So all linear combinations of these will be solutions as well, right? So that means that our null space is equal to the span of these two vectors.
So is the column space just going to be all the translations of the null space then? Oh wait, no, they're in different spaces.
Yeah, so they are really different objects, right? So this information doesn't tell us about what the column space is going to be, right? Yeah, so let's just note that this is a subspace of R5, right? Our vectors have 5 entries. So this just makes up our null space. This is the null space. And then the column space, remember, is just the it's just the span of the columns, right? So here we have, if I want to label them, I'll just put some labels on them. I'll just call them A1, A2, A3, A4, and A5. to write down the column space is not that hard. We could just say, oh, it's the span of A1 through A5, right? And that would be it. But we have more information than that. We know that A3 and A4 can be written as linear combinations of the others, right? Because of the form it's in. It's not hard to see that. So we might want to just exclude those because they're not necessary, right? So note that, so now we're talking about the column space. This is the span of A1, A2, A3, A4, and A5, where those are just the columns. But also we know that A3 can be written as, let's see, it would be negative negative 3 times A1. Sorry, I can do this at the same time. Okay, negative 3 times A1 plus 5 times A4, right? That would give us, no, A4, what am I doing? 5 times A2, no, 3 times, okay. Let me recalibrate. Okay, A3 is negative 3 times A1 plus 2 times A2. Okay, there we go. And then the same for A4, we can write it as a linear combination. It'll just be 5 times A1 minus A2. Yeah. Okay. So that means they're unnecessary. So we're just going to throw them out, and we can write that the column space is just the span of those necessary vectors, which are A1, A2, and A5. Right. And notice that these correspond to the columns with pivots in them, right? They're just the columns with pivots. The others were unnecessary.
So to tell like what the dimension of the column space is going to be, you can just look at the pivots. But is there an easy way to tell what the dimension of the null space is going to be? Because like, I mean, if it's a square matrix, then we have to take 0 to 0. But like, is it like about like what gets zapped into nothingness? Like if we're going from like R4 to R3 kind of?
Yeah, exactly. It's about what collapses, right? So how much collapsing do you have? And this is essentially how we figure that out. It's just solving the homogeneous system. So there is a way of quickly telling that, but we'll get to that later, I think in the next section. So yeah. Okay, so I'm gonna have you guys do a couple of practice problems. So just determining the null space and column space for a couple of matrices. So I want you to determine null space and column space for, whoa, oops, the following. So I'll just label these A. Right now, I'll use numbers. Okay. So here we have 1, 2, 3, 4. This matrix. 1, 2, 3. And 2. There we go. Okay, so start working on these, and then we can talk about solutions. Okay. Okay, are there any questions about these? I can give the answers if you want, or so you can check your answers, or we could go over them.
Yeah, let's go over them. I believe it's better.
Cool. So, sorry, 1 second. Yeah. Oops. Let's see. So starting with 1, if you row reduce it, you should get just, so let's do this guy down here. If you row reduce this, you should get the identity matrix. You guys agree? Okay, cool. So you get the identity matrix. That means that the column space, the span of the columns is going to be all of R2, right? Because these two vectors span R2. And then the null space is only going to have, so the homogeneous system is only going to have one solution, and that's the 0 solution. So the null space is only going to contain the 0 vector, right?
Oh, do we have to write that set notation when writing the?
Yeah, I prefer it.
Okay, even though there's only like one vector.
Yeah, yeah. This is, yeah, the best way of writing that. Okay, so that covers example 1. For example 2, this is a 1/3 matrix, right? So, and it's already in reduced row echelon form because there's only one row, only one possible pivot. So let's start with the column space. The columns are each just one-dimensional numbers. And so the column space is a subspace of R, and it's going to be all of R since we have non-zero numbers there, right? And then the null space of A, remember this is just solutions of AX equals 0. Right, so writing that in terms of this matrix, I'll just use X, Y, and Z as my variables. So we have this is equal to what we'll get out of this matrix multiplication or vector multiplication is just 0, right? So it's, instead of writing the 0 vector, because there's only one entry, I'm just gonna write normal 0. And on the left-hand side, if we multiply this out, we get X plus 2Y plus 3Z equals 0, right? So this is actually, we could write this down as, I need to move this over a bit maybe.
Pardon me.
What's that?
It says 3y instead of 3z.
Oh, it does, yeah, thank you.
I just want to make sure it's clear for like when we go back over the notes.
Right, yeah, it's good to point out typos because that can be confusing. Right, so it is the vectors in R3 that satisfy this equation, basically. And notice that this is actually a plane in R3, right? That describes a plane that passes through 0, right? So the 0 vector is in there, so it is a subspace. Yeah, and then the last one is the most involved. We do have to row reduce this matrix, right? So I guess the first thing to do would be to multiply by -1 the first row. And then we want to take row 2 to row 2 minus 2 row 1 to eliminate that guy. Let's see, for the null space in problem 2, why didn't you write a span of parametric vectors? Oh, yeah, you could have. It's just because it's like this simple type of problem, I kind of wanted to point out that it's a plane. But you can, yeah, just write it out like normally. Yeah. Okay.
So then for number 2, would that mean like there are like how many free variables would this have then?
It has 2 free variables, right? Because
2. Yeah.
yeah, because it can only possibly have 1 pivot, and there's 3 variables. So in terms of how I wrote it, y and z are free variables. You can just pull them to the other side, write x in terms of that, and then you have these, I guess, 2 vectors, if you want to write it that way. Okay. Right. So I realized that there was something that I meant to mention at the beginning of class. So it turns out that not many people, or almost no people, are showing up to the problem sessions. So I want to, I don't know, I want my TAs to like be doing something productive and like helpful to the class, not like, you know, sitting in an empty Zoom room, because so I don't know what to really